final point of discussion that we had was that, let's say you're pushing something with a constant force, and then you start pushing harder on that particular object. So this is the force versus distance. So for a little bit of ways, you push it with some force. Maybe the first meter you're pushing it, you give it force. And then for that next half meter that you're pushing something, you push it faster or with more force, okay? Then the area under that graph is equal to the work done. All right, so that's a final thing. You put a little star there. We might not have a lot of homework problems that deal with that, but there definitely are AP questions that deal with that concept right there. So, okay, let's talk about kinetic energy and potential energy. Kinetic energy is energy of motion. What do you think the kinetic energy depends on?
Velocity.
It does depend on velocity. As the velocity goes up,
So does
kinetic energy goes up. Okay? So that it's a proportional relationship. Well, at least they're directly proportional. It turns out, the way we have kinetic energy defined, it's a quadratic relationship. If the velocity goes up by a factor of 2, the kinetic energy will go up by a factor of 4. If the velocity gets multiplied by 3, the kinetic energy will be multiplied by 9. Did you catch that? Okay? Multiplied by 5, kinetic energy will be multiplied by 25. What else do you think kinetic energy depends on?
mass?
Yeah, how much mass there is. That happens to be a linear relationship, and we have a multiplier there of 1/2. So 1/2 mass times velocity squared. That is linear or maybe sliding kinetic energy. Now let's say you've got something, let's say a bar attached to some sort of hinge or pivot. You could conceivably break that bar down into all of its tiny pieces. And as this rotates around, you've got this piece which goes around, this piece which goes around, this piece which goes around. And because these different particles are at different radii, okay, then they're going to have different linear speeds. This one's going to be going around kind of slow. Remember the teddy bear? Kind of slow. But this teddy bear here is going to be going really fast. Remember those videos? Okay? So we can talk about the rotational kinetic energy. All right? This thing, I mean, this point right here comes back around just where you started, ends up where you started from, right? So if something is spinning or rotating, then it's 1/2. What's the rotational equivalent of mass? Moment of inertia. We could say this is inertia and then movement, rotation of inertia. So that's I. And the rotational equivalent of velocity? Yeah, omega squared. So that's your rotational kinetic energy, K rho. And then, think about it. If something is rolling, oh, sorry about that, James. It's laying on the table. Rolling. Go ahead and roll that over there. Do y'all have a ball over there?
Here.
I'll give you a bottle. No, I'm not gonna do that. Sure, roll the pencil. All right. Didn't break it, did I?
No.
Thank goodness. Did I wake you up?
I guess.
Sorry about that.
It's fine.
All right. If something's rolling, notice, is it moving linearly? Yeah, it's moving along that line there. But what is it also doing? It's rotating there, yeah. So if it's rolling, you're going to have both kinetic, you're going to have the linear and you're going to have the rolling. So we say K rolling is 1/2 mass velocity squared plus 1/2 I omega squared. So throw me that ball. 1/2 mv squared plus 1/2 I omega squared. Now think about this. Imagine if this particular ball is sliding along at 1 meter per second. 1 Mississippi. Okay? Think about how much kinetic energy it has. Now, think about the same ball, but it's rolling along at 1 meter per second. Okay? Which is going to have more kinetic energy? Sliding at 1 meter per second or rolling at 1 meter per second?
Rolling.
Why rolling?
Nearing the same speed, but also adding.
It's also going to have the 1/2 omega squared. Absolutely. Has anybody ever gone bowling?
Yes.
Do you know how to get more pin action when the bowling ball hits the pins so that the energy from the ball transfers to pins and they go
Yeah, like
Spin
the
it
wrist.
faster?
spin it?
fling the wrist.
All right? If you just get the ball and you just dead arm it there and it just sort of ends up kind of sliding along the lane, okay? Then that energy will just it's pretty much just sliding. It hits the pins, it'll knock 1 or 2 pins over. The energy gets transferred, not a whole lot of motion going on. But if you're able to spin it, now if you spin it, you normally have to kind of angle a little bit to the side because it'll kind of start to curve a little bit. But if you spin that ball, when it hits those pins, then you get lots of pin action, and they'll bounce back around and stuff like that. The ball's kinetic energy will turn into the pin. Both of those combined will turn into the kinetic energy of the pins, and they'll knock each other down, and maybe get a strike or pick up that spare. Okay, so that's why if you look at the professionals, they're not just sort of. I mean, I'm really good. I'll tell you, you probably are too. If you're a bully, you get that straight down the line, but it might just go boom, 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 and knock those down, knock them all the ones down in the middle, and then you end up with like a split. Okay. So anyway, something to think about. If you're playing soccer, if they kick the ball and it's spinning and it hits you, if it's spinning, it'll have more energy. It'll leave more of a welt than if it's just not spinning. There you go. What else can we say? All right, so that's kinetic energy. Let's talk about potential energy. Oh, pull out your AP formula chart. I think those are on the chart. Maybe this one and this one. I guarantee you this one is not on it. I want them both combined.
Yeah, they're both here.
1/2 MB squared and 1/2 I omega squared. Yep. Left hand column.
Wait, where'd you see the second one?
There's that one and the other one right down there.
Oh, MV squared. Oh,
A
yeah.
lot of this is all the linear stuff, and then this is all the rotational
Anything
stuff.
that has.
Wait, I see this one. I don't see the
Yep.
other one. Which other one are we looking for?
Got it? They're both.
Yeah.
Man, we are knocking this chart out, aren't we?
Mm-hmm.
We are getting real close. Okay. Well, all right. Let's keep going. Potential energy. Here's the formal definition of potential energy. Okay. The change in potential energy of an object is equal to its mass times the acceleration due to gravity of whatever planet it is on times the change in its y position. And you're like, okay, that's kind of boring. I want to show you the easy way that when I learned physics, I didn't learn this advanced, awesome physics that you're learning. Okay, so this is Mr. Goddard's old way, and this is the formula that I just had memorized. You've got an object that's above ground, okay, and then its potential energy, U equals mgh. That's just how I remember. U equals mgh. Mass times gravity times height. Makes it real nice and easy, okay? Times whatever height that is. There would be some problems with that though, okay? And the problem was, who determines what that height is? You know what I mean? And the follow-up answer is, well, you do. You figure it out. Because what happens if you have something like this? You've got a hole, right? And then you have maybe a tower. And this object is right here above the hole. And this object is right here, and it's above the tower, okay? I mean, do both of those have the same potential energy? I mean, you know, if this thing, let's go and falls, you know, eventually it's going to get all the way down to there, and it's going to have a lot more kinetic energy, okay? This one's going to fall, and it's going to hit right here, right? And so, now technically, so if I were to determine that this is the zero line. I could do that, or I could determine that this is a zero line or this is a zero line. And so that led to lots of issues. You know, do I call this the height from here to here, or do I call this the height, or do I call this the height? What does it mean? And so the best solution to that is don't consider an object in isolation. Okay. Say, whenever you have an object from, you know, wherever it is to wherever you are now, look at the change in the height, and that corresponds to the change in the potential energy. So think of it almost like a before and after. If it was here on the ground level and you moved it up here, then now it has changed in its potential energy. If the object was here and then you moved it up to here, a very small distance, very small delta y, then it's at a very small change in potential energy. If it was down here in the bottom of the hole and then you moved it up here, then its change in potential energy is proportional to that. So that's why your formula, if you look on your formula chart, I think it's got this right here. The change in gravitational potential energy is mass times gravity times the change in its y component. So that kind of makes everything real nice. Is that on your formula chart?
Mm-hmm. It's the first one in the right column.
First one that, okay. There's some interesting things that come about because of this. What do you notice that the potential energy depends on?
Height.
I wouldn't say height, I would say
The change.
it depends on the change in height. Okay? What does G represent? The acceleration due to gravity, okay? Yep. And M, mass. So more mass,
Weight.
more potential, which you can correspond to mass times gravity and say that corresponds to the weight. By def, that's what we call the weight. But yeah, more mass, more potential energy seems to make sense. What does it not depend on?
Velocity.
Velocity, yep. Speed. Yep. It also does not depend on the path that the object takes.
You could do this and it doesn't matter.
That is correct.
Are you, if you
Can you
were-
hold on? Can you do that again for the camera, please?
No.
So if you were like, lift a pencil, like this, are you measuring
Where did you lift it from?
here?
Okay.
And move it here.
It's from
Are you
there to
measuring
the
this,
table.
or are you measuring height?
If we're talking about the change in potential energy, we're talking about the height.
So you would just move that.
Yep. So so she said from here up to over here, you know, moving it like that. Yeah, it's the y component is all that matters with the potential energy. Also, notice, let's say I go from here and I go up to here, I've got a change in energy of 10 joules, okay? 0, and now it's 10 joules. Watch this. This is what Raina did. Go down here. Right here. Stop. Stop at the same place. What's the change in potential energy? 10 joules. Right. It doesn't matter about the path, okay? In terms of the change in potential energy. It just depends on where were you and where are you now. Now there is that much potential energy between where you were and where you are now. Yeah, in the middle you probably spent a whole lot of energy moving that sucker around, or you may not have. But I'm not measuring how much energy you used. I'm measuring how much energy was in the ball down here and how much energy does the ball have right now. So that's kind of an interesting, fun thing. There's some applications there. There's also the potential energy in a spring. Where'd that spring go? So as it is right now, just there on the table, spring doesn't have any potential energy. I'll put it sideways since that way we don't have to deal with gravity. I stretch it out right now. If I release it, there's going to be some energy. There's going to be some mechanical energy. There's going to be some work going on. Okay, force times distance. Okay, right. And you see the potential, right? Oh, it just wants to go back there, right? So there's potential energy. What does that depend on? Make sure I get this right here. The potential energy is in a spring It depends on how far you stretched it, okay? So that's x. Turns out it's a quadratic relationship. It also depends on how springy or how hard or soft that spring is. That's the spring constant, K. And we found out that we've got a 1/2 multiplier in front of there, so 1/2 kx squared. That's the potential energy in a spring. We were filling in all the gaps today, aren't we? Yep. That's second to last one in the left-hand column. So it's very clear to make sure that we understand this is the potential energy due to gravity. Okay? And it's not just potential energy, this is the change in potential energy due to gravity. If you want just the pure, how much potential energy is there due to gravity, so U big G, alright? So the potential energy between an object and another object, so we're talking about something like this ball and the earth. Technically, when you're finding the distance between two objects at this point, this is the gravitational potential energy between the center of this sphere and the center of the Earth's sphere, okay? Because at that point, when this is at the very center of the Earth, then its potential energy is 0, okay? But this is equal to negative G, that's that gravitational constant, times the mass of the juggling ball, mass of the Earth, divided by R, the radius, where radius is the distance between their centers. And I think that one is also on your formula chart. Second column, last on the bottom, all right? Most of the times, you're going to be able to figure out what this is. But if you want to figure out between, a satellite and the Earth, you can figure out what is the potential energy of that object. Okay. I think we're ready to do some problems together. Can I get one for the other? Can you get that one? All right. What's up first? Quick check. Go to the bobsled one. Two-man bobsled has a mass of 390 kilograms. Starting from rest, the two racers push the sled for 50 meters with a net force of 270 newtons. Neglect friction. What is this sled's speed at the end of the 50 meters? All right? Now you can think about this. Oh, we're going to do kinematics, find the acceleration, initial velocity, final velocity. So, you know what I'm talking about? Acceleration, blah, 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 blah. That is one way that you can do this. We'll try to draw a bobsled. One guy, he's inside, the other guy's going to be pushing it. Or that guy's on the other side. Mass of 390 kilograms. Starting from rest, which velocity is 0. They push it for 50 meters. So from right there, right here. With a net force of 270 newtons. So that entire time, 270 newtons. What are they wanting us to find?
Final velocity.
Final velocity. So V, or VF. So there was the old kinematics way with dynamics, forces, acceleration, your kinematic formula, V squared equals V naught squared plus 2AD. But we can also think about this in terms of like an energy problem, okay? Think about the energy before, think about the energy afterwards, think about the work that they put into it, okay? So initially, what's their energy? All right, maybe should be more specific. Sorry about that. Kinetic energy. What's their initial kinetic energy? Zero. Kinetic energy is 0. Potential energy.
270.
Now, they're good. Well, you say, Mr. Guy, you're not giving us information. What's the height? And the answer is, I'm going to declare that this is the 0 potential energy. Okay. So, guess what? Their potential energy is also 0. Okay? This is their initial energy plus the work done is going to equal their final energy. Alright? So we've got their K final plus their UG final, potential energy final. Now we'll think about that for just 1 second. What's their potential energy at the end? 0. And we would normally say, plus there's a thermal energy change. But that thermal energy would have been due to the friction, and they said just ignore friction for right now. So in reality, we're essentially doing energy initial plus the change in energy equals energy final. And as we all know that the change in energy is equal to the work done. All right? So work done is the force times the distance times the cosine of the angle in between them. So the force vector is to the right.
There's no angle.
The displacement, there is an angle.
But it's 0.
Its value is 0. So force times distance times the cosine of 0 equals, we now have a new formula to use for kinetic energy. 1/2 mass times velocity squared. Alright? And what we're going to do is we're going to solve this for velocity, so we only have to do one thing all at the same time. So, oh yeah, we know that cosine of 0 is 1. So solving for velocity, the velocity is going to equal square root, I'll multiply both sides by 2, so 2 times the force times the distance divided by their mass. Gracie, does that make sense? Multiplying both sides by the 2,
Mm-hmm.
dividing both sides by the mass? Yes.
Okay, so I get that, I get that bottom part, but what does the E initial plus delta E, what does that have to do with?
Good. This is me sort of backing up. I might have started here, but this is what I'm saying is that the initial energy of the system, kinetic and potential, okay, plus whatever the change in the energy is equal to the final energy. It's an abstracted version of this right here.
Yeah.
It's just sort of like the pre-step. And it's nice because it sort of follows, it's sort of a pattern we've had in this class. Where you start plus your change equals where you end. And that's true for energy as well. Anybody have a final velocity there for us?
No. 8.32.
Okay. I'll just say 8.3 meters per second. So I'm not going to do a million of these problems just because we don't have time for that. lots of variations. But for your homework, they will have different forms of initial and final, and you'll just have to figure out some point in between. In this particular problem, they gave us the force and the displacement. Maybe in one of your homework problems, they'll give you a graph to find what the work done was, but you just look at the area under the graph. All right, let's keep going. Hey, that's a much better bobsled picture. And they came up with 8.3 as well, so that's pretty reasonable for us. Let's see. Harley, can you read to us this one about the plastic and the heavy cart?
A light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter. Starting from rest. After the force is removed, the kinetic energy of the light plastic cart is blank.
Mm-hmm.
That of the heavy steel cart.
So is the kinetic energy of the light cart greater than, equal to, or less than, or can't say, depends on how big the force is. Does this one have more kinetic energy or less kinetic energy than the heavy steel cart? Just shout out a gut level response. Less. Really, it's less. It's going to have less kinetic energy, right? You're sort of like, it doesn't weigh as much, okay? Kinetic energy depends on mass, right? Guess what it also depends on? Velocity. All right? These are designed to trick you up a little bit. Think about the initial energy, okay? Initial energy plus whatever the change in the energy is going to equal the final energy. So they're both starting from rest. So what's their initial energy? 0. The change in energy is the force times the distance, times the cosine of the angle between them. But since this case, the distance distance vector is in the same direction as the force, we could just say force times distance. Okay. In fact, when I took my physics class, I did not know work equals force times distance times cosine theta. I just would have said, oh, work is force times distance, because they never gave me any problems with the angle. But they will for you. All right, so force times distance equals, what type of energy does it have at the end? Kinetic. Kinetic final? Kinetic final. So, what's the relationship between the kinetic energies? They are the same.
Actually, have to push the same route.
Yeah, but what's different about those two carts?
Their mass and their velocity.
Their mass and the velocity. Okay?
Like the velocity.
Do you want me to get the? Well, we were running out of time. Just imagine if I'll get 2 Hot Wheels cars, the one heavy truck and the one really light dollar store car, right? Okay, and I push them both at the same force. Okay, the heavy one, it's got kinetic energy 1/2 mv squared. It's got a really high mass, but its velocity is going to be smaller. Okay, the light car, the little dollar store car, is going to have a very small mass, but its velocity will be higher. Does that make sense? So the lighter car is going to be going faster than the heavy car, but they both have the same kinetic energy. All right. Next one. Each of these boxes shown is pulled for 10 meters across a level, frictionless force. I don't think this one is. You don't have this one. That's fine. Who cares about that one? I don't care about that one. Let's talk about potential energy. Yep. Oh, this is nice. Might be a thought if you are ever going for a hike or anything like that. Okay? You're going along, and this is like my family, your little brother or sister, my case, little sister, she says, oh, let's go this way. And she zips up here, and then she zips up that way, and then me, I'm like, oh, I'm going to go climb up that like rock cliff, right? And I go here and I climb up this part right here. And we both get to the same part, right? And we could both say, we both our potential energy has changed 160 kilojoules. It doesn't matter that she went up a short little ramp and then another short little ramp, and I walked straight for quite a while and then climbed up the rock cliff. We both have the same change in potential energy, okay? Now, I'm huffing and puffing, and she's just kind of like, you know, bebopping around. She seems to have more energy. What's different is the power, okay? And we'll talk about that later in the chapter. So let's talk about this. Rank in order from largest to smallest the gravitational potential energy of these balls.
Are we saying in this instant?
At this moment of time, right? This one has a velocity going up that's really large. This one has a velocity going up that's going large. This one has zero velocity. This one's falling down, okay? Now, your first thought is, what role does the velocity play in the gravitational potential energy? None. Huh, okay. So just ignore those arrows. What does matter with the potential energy? Height. So who's going to have the biggest potential energy? 3. And then
2 and 4 are equal.
2 and 4 equal, and then
1.
you are correct. Still got another minute or two, so just hold on. All right, Gracie, read this one to us.
Starting from rest, a marble first rolls down a steeper hill, then down a less steep hill the same height. For which is it going faster at the bottom?
We're going to assume that there's no friction, which friction normally would eat up some of the energy. Okay? Is it going faster at the steep hill, faster at the less steep, same, or not totally? Can't know without knowing the mass of the ball, which is the same in both cases. What do y'all think? Like, what's your non-AP physics, just gut level response? It's going to be going faster on the steeper slope, right? Okay? But think about this. It's got potential energy here, and this guy over here has the same potential energy here. All of that potential energy is now kinetic energy. Okay? All of that potential energy is now kinetic energy. And what is kinetic energy based on? Mass times velocity squared. What does kinetic energy depend on over here? Mass times velocity squared. It'll assume it's sliding. We could have said 1/2 I plus 1/2 I omega squared, but we only have about a minute or two left at this point. So the 1/2 are the same. The masses are the same. So guess what is also the same? The velocity is the same. Okay? So you might think, oh, steeper slope, it's going to be going faster. It will not. Okay? Steeper slope and larger slope, it'll be going the same speed. Now, Kevin is like, that's not what I had when I played with my Hot Wheels. All right? The part of the answer to that is that the friction, okay, is going to eat up some of that energy. Okay? So if we make this a little bit more realistic, if this, say, has 100 joules of potential energy down here, and this one, there'll be frictional effects, okay, but it maybe has 98 joules here to turn, of kinetic energy. This one, since it's longer, will have 95 joules of kinetic energy, and so therefore it will be going slower if friction comes into play. Okay, because some of that potential is turned into both kinetic and thermal. Did you play with that on the lab the other day?
Yeah.
When you turn thermal on, you saw it start eating into the total energy. Okay? I really love it when I can do that with y'all, but I was going, so. Anyways, still, since we didn't finish this, I'll push that homework till Monday probably. We'll wrap up this discussion. Still, be ready for 10.5 and 10.6 tomorrow because we're almost done with this.